Okay, now we talked briefly about being able to determine the mass of an electron. Um, what that does for us, it gives us a model for what we expect the atom to look like. And the model that I'm going to use is what's called the plum pudding model. Okay, and the plum pudding model, apparently I've never had plum pudding, but one day I will. The plum pudding model is, well, apparently plum pudding has chunks of plum in it, hence plum pudding. So the plum pudding model has these electrons, which we were able to measure previously. And we believe those electrons are then in this goo, okay? And this goo has charge, okay? So in the case of this atom, which has 4 electrons floating around there, our goo would have a total of +4 charge, okay? So because we're able to pull out the electrons, and we notice that the electrons have very, very small mass compared to the overall system, excuse me, I'm just adjusting that, we figure that the rest of the matter is kind of this blah that floats around there. Because, you know, we look at matter and we think it's continuous. We think that it's one big chunk, okay? We know that that's wrong now, but it doesn't seem that far-fetched at the time. Well, there's an experiment that's created to test this model, okay? And the idea is to take this particle, or this, not particle, this atom, and the material they choose, the atom that they choose is gold. They take a sheet of gold, they flatten it out as thin as they possibly can, okay? So you have basically this goo just all the way down there with these electrons floating around in there. So they figure it's a solid wall with very small negative charges in there, but big blobs of positive charge in there. So they take that model and they bake off alpha particles. So they kick out an alpha particle. And if you remember what an alpha particle is, it's got 2 protons and 2 neutrons. They bake that off and they fired it at this sheet of gold that they flattened out. And gold is used because it's highly malleable. You can flatten gold out pretty thin. So what they predicted would happen because of this model is that any particle that has a positive charge that approaches this goo would be deflected. It wouldn't necessarily be stopped, but it would be deflected. It wouldn't go straight through. It would go at all these different angles. Okay? But every particle would be deflected. It didn't turn out that's not the result they got. As a matter of fact, the result they got, which they expected to have it go everywhere, they noticed that almost, well, I should turn and face. The result they got was unpredictable. Almost every single particle passed through, no problem. Just went right straight through, no deflection whatsoever. Every so often, like 1 in every 1,000th of a particle was deflected. And some of those particles would end up, over here. But other particles were actually deflected back. Okay? So some serious deflection. So the plum pudding model was a failure. They said, look, that's not possible. That's not possible at all. But the interesting thing is what they've just done. Have you ever tried to measure something without physically measuring it? So, imagine, if you will, if you had an atom, and you wanted to measure that atom, and you wanted to try to determine the size, let's not say the atom, let's say the nucleus inside that atom. How'd you do it? Well, you couldn't grab yourself a tape measure, and you couldn't measure the atom that way, because it's just not possible. So what they ended up doing is they ended up continuing to run this experiment. You let it run over a long period of time, and you find out that like 95% of the particles that travel through that sheet are undeflected. So almost all of them are undeflected, but 5% are deflected. Okay? So what you know now is that of the volume of the atom, 95% of it's empty. And only 5% of it is occupied. Okay? So if you have a base understanding of the size of that atom, you can use the percentages to determine how much percentage of that atom is actually occupied and then what percentage of it is not. So when you're firing at it there and you get 95% of it to go through, you can make the assumption that your original model, which was 100% full, now only has 5%. Okay? So this 5% means that the volume of that atom is only has matter in 5% of it. So it completely changes our idea of what an atom is. What that does is it creates a new model. The new model takes a look at classical systems and says, hey, look, we know the size of our universe, not either one of those. Our solar system is massive, but almost all of it is open space. The volume of it is almost completely empty. There's only small chunks of matter inside our solar system, like the sun. Takes up only a small chunk of that space of the entire volume of our solar system. So why not presume the atom is the exact same model? Okay? So we come up with this model of an electron orbiting the nucleus, which contains all of our positive charge. Okay? So we got this electron orbiting a nucleus much in the same way a planet orbits the nucleus. Okay? So classical mechanics is appeased. It's like, well, if it can't be just filled with blob or goo, why not make it a planetary model? Why not go back to Galileo, to Kepler, and go with that model? Well, the problem with this model is that what happens if I steal some energy away from an electron? What happens if that electron gives off a piece of light? Well, the electron would then decay. Okay? It would do something like that. So if I stole a little bit of energy off from it, it would start to decay and do this kind of orbital business. But the problem with that is that it would continuously generate light as it goes down to that state. And as a matter of fact, this constant light that it's generating is going to be in all sorts of different wavelengths. Well, we know that to be not true. We've already studied this phenomenon. This was done way before we had an understanding of what the atom was looking like. What I'm talking about is spectroscopy. If you take a chamber filled with gas and you run a voltage through that gas, what you end up getting is not all of these not all of these different colors of light. Instead, you may end up with 3 different colors of light, or maybe 5 different colors of light, but not all of these colors of light. So we had this model. We thought that the model was correct because it follows classical mechanics, but when we apply it to things that we already know about spectroscopy, we run into a problem. It doesn't seem to follow any of our models. So we have to throw that model out. So we've already thrown out the plum pudding model. We're throwing out this classical model. And the next model that we come up with is what's known as the Bohr model.